look loud. All right. Thank you. All right. So we are. So this is now chapter 7, section 7.1. All right. So it's about graphs of normal distribution. Normal probability distribution. So this is normal probability distribution. All right. So let me just remind you, I mean, the last 2 chapters, like in chapter 5, we discussed probability distribution of a discrete variable, right? In chapter 5, sorry, chapter 6. So chapter 6. So we discussed the probability distribution of a discrete variable, distribution of a discrete variable. Right, that was section 6.1, right? The section 6.1, and then in 6.2, 6.3, we discussed, of course, a binomial distribution. Binomial. So binomial distribution in section 6.2 and 6.3. So of course, a binomial distribution, guys, it's a probability distribution of a discrete variable. Remember the number of successes R. So the number of successes R is it's actually a discrete variable because it takes only a finite number of values. So now, so in this chapter 7, so we're gonna discuss probability distribution. So probability distribution of a continuous variable. So I will explain, of course, what I mean by continuous variable, but just so you can see the difference between chapter 6 and chapter 7. Chapter 6 was about discrete variable. So in this chapter 7, we're going to talk about continuous variable. And in particular, we're going to discuss this normal distribution. So in particular, we're going to discuss this normal distribution. All right. So so in chapter 6, we discussed the particular case of a binomial distribution, particular case of a discrete variable, and here we're going to discuss normal distributions. All right. So what's a normal distribution? Well, I would say, I mean, normal distribution, this is like one of the most important probability distribution. Okay, this is one of the most important. Okay, so this normal distribution is normal distribution. This is one of the most important. Is one of the most important probability distributions. Okay. All right. So before introducing this normal distribution, let me just remind you, like for binomial distribution, right? So for binomial distribution, you know, you can always graph the binomial distribution, and we said we can use the histogram, right, to graph binomial distributions, and then so you get something which looks like, for example, so the graph. So to graph a binomial distribution, you know, we use histograms. Right, and then we said, so when you graph your binomial distribution, the graph. So let's say the graph is going to look like something like this here. So you have something like this, for example. This is your histogram of your binomial distribution. But the thing is, we said the area end of the graph is always equal to 1, right? Remember, we said, like, when you graph your binomial distribution, the area, so this area here, end of the graph, is equal to 1. Area under the graph is equal to 1. Okay, which is, so when we say 1, we mean 100%. Okay. Now, the thing is, so in general, so let's forget about binomial distribution. So now, in general, so if you have a graph, so if you have a graph, let's say we have a graph, and for example, the following, let's say we have the following graph, like this here, right? For example, this, okay? And let's say the area under this graph, so this area right here is equal to 1. So this area here, area under the graph, is equal to 1 or 100%, right? Then this graph actually can represent the probability distribution of a continuous variable x. So the idea is, so you see you have your horizontal axis. So let's call the horizontal axis the x-axis, right? So this graph, so whenever you have a graph where the area under the graph is 100%, then the graph will represent, so the graph represents probability distribution for probability distribution of a variable, actually continuous variable x, continuous variable x. So now, so how does this work? Well, the thing is, so if you want to find, let's say, so you have such a graph and you want to find the probability of x. Let's say we want to find, so we want to find the probability of x, right? So what we do is we take, so to find this probability of x, we take the area under the graph. So to find the probability of some x, probability of let's say x x or x0, then we measure, let's say, the area so we measure the area under the graph for x less than x0. So for example, let's say I have this graph which represents some probability distribution. I have this graph right here, okay? And again, as I said, the area of this graph here under the graph is equal to 1 or 100%. And let's say you have some x0 somewhere here, right? This is x0, let's say. Of course, the horizontal axis, that's your variable x. Now, if you want to find, let's say, the probability of x0, so what we do is we take the area under the graph, which is for x less than x0. So we're going to take the area under the graph, which corresponds to x less than x0, right? So here, you see this area here, this is where your x, so here x is less, right? It's less than x0. It's on the left side of 0, okay? So the probability of x0 is just the area to the left of x0. So probability of, say, x0 is just the area under the graph, area under the graph, to the left of x0, left of x0. Okay. Anyway, so the idea, guys, is that whenever you have a graph such that the area under the graph is 1 or 100%, right? Then the graph actually represents the probability distribution of some variable x, of some continuous variable x. And to find the probability of some x, let's say, or for some x0, so what you need to do is you need to take the area under the graph to the left of this x or x0. Okay. So that you see this, so the area, this area right here, this red region, the area here is equal to the probability of this x0. Anyway, so let me now introduce this normal distribution. So so the important properties of the normal distribution are the following. So important properties of normal distribution. So when you have a normal distribution, then the graph of the normal distribution would be bell shaped. Okay, so first, the graph of a normal, whenever you have a normal distribution, then the graph would be like a bell shaped of a normal distribution is bell shaped. And actually the highest point of the graph is corresponds to the mean, and the highest point point of the graph of the graph is at the mean. So so we're gonna have something like this. So your graph is gonna look like so as I said, it's bell shaped. So the graph would be like So this is your variable x. Of course, the horizontal axis, that's your variable x. Okay, you have some variable x. Like in binomial distribution, your variable is the number of successes r, right? Here, so we have this variable x, and so the graph of this probability distribution is going to be bell shaped. So we're going to have like something like this, which looks like this. And the highest point, okay, so the highest point would be, so here's the highest point of the graph, right? So the highest point corresponds to is actually at the mean. So I'm gonna denote the mean by mu. So here the mean, mu, okay? And so here is my mean, mu. So this is mu. It's again, this is the mean of when we have a population, right? So we denote the mean by mu. So this is a Greek letter, and so it's called mu, mu, right? So the highest point is, as you can see, is at the mean. And of course, the area under the graph is equal to 1 or 100%, right? So the area, so the area under the graph, or the curve under the graph is equal to 1 or 100%. Now, if you want to find the probability of some x, so we have some x, and let's say you want to find the probability of x. So what we do is we take the area to the left of x. So to find the probability of x, so p of x. So this is the probability of some x, of the variable x. So probability of x. So what we do is we take the area to the left of x. We take the area under the graph, of course, under the graph to the left of x. So for example, so I have, again, this is my graph. Here is my normal distribution, which is, so it's the graph's supposed to be bell shaped, right? Like this, and the highest point is the mean, right? Somewhere here's my mean, mu, right? And let's say I have some x here, some value of x. Here's my x, right? And I want to find the probability of x, right? I want to find p of x. Find p of x. So all I have to do, so if I have the graph, is to measure the area to the left of x. So the area to the left of x, of course, would be this area right here, right? Under the graph to the left of x, right? So that area, that's actually equal to the probability of x. So that's, so p of x is equal to, as I said, so this area right here. So the area, that's your p of x. So area to the left of x. Of x. Anyway, so next property of a normal distribution. So we have a graph which is bell-shaped, etc. Highest point is at the mean. If I want a probability, or if I want to find the probability of some x, all I have to do is to take the area to the left of x, right, etc. Now, the next property is the following. whenever I have a normal distribution, so for a normal distribution, distribution with mean, so I'm gonna denote the mean of normal distribution by mu, the population mean, mu, and mu. This is mu, right? And standard deviation sigma, and standard deviation sigma. So this is sigma, lowercase sigma. It's also Greek. Sigma, right? Then we have something which is, analog to this Chebyshev's theorem. So then we have the following. Then we have the following. So in the graph, so here's your variable x, and then so this is my graph of my normal distribution. Oops, this is really bad. So it's again supposed to be bell-shaped. So we're gonna have something like this here. Okay, the highest point, let's say this one here, it corresponds to the mean. This is a mean mu, right? But then we know we know, for example, when we have a normal distribution, then so if you take mu plus sigma, so this is mu plus sigma. Sigma, again, that's the standard deviation, right? Again, the mu, that's the mean. That's the mean of this normal distribution. And then this is your sigma. That's the standard deviation of your normal distribution. Now, so if you have a mu plus sigma and mu minus sigma, then we know the area of this region between mu and mu plus sigma, that will be 0.34 or 34%. So this is so the area of this region right here, this would be 34%. 34%. Right. Of course, when I say 34%, that's 34%. That's 0.34. Right. Now, between mu and mu minus sigma, it's the same thing. It's also 34%. So the area of this region, right, this is 34%. Okay. Now, if you take mu plus 2 sigma, so let's say here, this is mu plus 2 sigma, and here it's mu. I'm probably going to need more space here. Yeah, let me just probably erase this right here because I'm going to need more space. Something like this. All right, so we have mu plus 2 sigma and mu, this is mu minus 2 sigma. Right here. Then the area of this, like this blue region here, that's actually equal to 13. This is 13.5%. So when I say, of course, 13.5%, that's 0.135. Now, between the same thing here, between mu minus sigma and mu minus 2 sigma, I have the same thing. I have the this 13.5%. This is also 13.5% here. Okay. Then if you have now mu plus 3 sigma, this is mu plus 3 sigma, and here it's mu minus 3 sigma, right? Again, mu, that's the mean, and sigma, that's the standard deviation. All right, so then the area of this region between, you see the region between mu plus 2 sigma and mu minus this one here, you know, the green, this green region. So the area of this green region is actually 2.35%. So 2.35%, of course, that's so 2.35%, that's like 0.0235. Okay. And the same thing on the other side. So on the other side, you see this region right here, between mu minus 2 sigma and mu minus 3 sigma. That's also this is also 2.35%. Okay. The thing is, guys, you need to keep in mind here is that you see the graph, the graph of your normal distribution here. It's gonna approach, you know, it's gonna approach this x-axis, right? It's gonna be very close to this x-axis, but actually it never doesn't touch this x-axis. There's no intersection between your graph and your x-axis. So here there is no intersection. There is no intersection between the graph and your x-axis. Okay, there's no intersection between the graph and x-axis.
So the whole entire 100% is not technically used in the graph.
Yes. So yeah, that's very good. So you see, like, absolutely, that's a very good point. So you see, like, the sum of all these areas. So of course, because you know the mean is like the mean is like the center of, you know, here it's like the center. Your graph is symmetric about, you know, this about the mean, right? So to the left of the mean you have 50%, and to the right of the mean you have 50%. But as you can see, if you do, you know, if you do this 34% plus, you know, 13.5% plus 2.35%. Okay, so like to the left of the mean, for example, here. So 34 plus 13.5 plus the 2.35. So that will be equal to so that's equal to 40. Let's see.
49.85.
Yeah. Yes, absolutely. It's 49.85%. So it's not exactly 50%, right? Because your graph is supposed to, I'm sorry here, I need more space. Okay, let me just erase this. So your graph is supposed to continue like this here. Okay, it's gonna be, you know, it's gonna be very, very close as you want from the x-axis, but it doesn't intersect the x-axis, right? So like here, there will be like, so like the area of this region right here is gonna be very, very small. Okay, it's gonna be very, very small, but still it's not zero. Okay. Yeah, so to the left of the mean you have 50%. To the right of the mean you're supposed to have 50%. The total area under the graph, of course, it's 100%. But as I said, so if you do this 34, no, so 34, you know, the 2.35 plus the 13.5 plus 34, that's not 50%. That's, but it's very close to 50%. The other side, the same thing, right? It's not exactly 50%. So you can continue, you know, after, you know, with the, after mu minus 3 sigma, you can have mu minus 4 sigma, right? So here, like, you can have somewhere right here, your mu minus 4 sigma, etc. Okay. But anyway, well, with this, I mean, with these areas, we can actually make some computations. I mean, if we assume that the distribution is normal, that we have a normal distribution, we can still have make some computations here. So, for example, let's do an example, right? So we're gonna use these, of course, these areas, the 34%, 13.5%, etc. Right? So yeah, so let's have an example. I'm gonna show you how to use those numerical values. So example. So let's say we have a normal distribution. So let's have a concrete example. So let's say the age of students in BCC is follows a normal distribution. A normal distribution. So here we have, so we have a normal distribution, and the age. So the age of the students follows a normal distribution. So the variable here is the age, right? So the variable x, the age of the students, that's our variable, because the variable x follows a normal distribution. So x follows a normal distribution. A normal distribution. Anyway, now let's say you know the mean and the standard deviation of this normal distribution. So let's say, for example, the average with, so the age of the students follows the normal distribution with average or with mean mu. So here it's the mean or the average of the age of all the students in BCC, right? So the whole population, not just a sample. This is not the sample mean, this is a population mean. That's why I'm using the mu, right? Because remember, guys, when we discussed the like different types of samples, we said there is a there's a population mean and there is a sample mean. So for population mean, we use the mu, right? This letter here. So with, let's say, with the mean or average equal to let's say 21 years. Okay, so that's the average age of the students in BCC. I say it's 21 years, and let's say the standard deviation of this normal distribution. So, and standard deviation sigma. So this is a population standard deviation. So it's not so it's denoted by sigma. Okay, it's not denoted by S. The S is when you have a sample standard deviation, but this is a population standard deviation. So this is a sigma. Again, this is called sigma. And let's say that the sigma is equal to 0.5. The standard deviation is 0.5. 0.5 years. Okay. All right. So let's say you want to find the percentage. So find the percentage of students with age less than 20.5 years. Okay. So, so I know the mean, I know the average, the mean is 21. I know the standard deviation is 0.5. I know that this age, the variable age follows a normal distribution, right? So because it follows a normal distribution, then we have these areas, right? So we have like, so now because the x, the variable x, the age. So because the age follows a normal distribution, so the age follows a normal distribution. So we know that distribution. So then we know the following. So we have, oops, sorry about that. So we know the following. So the graph of the normal distribution is going to be like, this here. So is it, again, it's bell shaped like this, and the top, the highest point corresponds to the mean. And what's the mean? We said the mean is, oops, so the mean is 21 years, right? That's the average. So the average age, right? So the 21. So here's my mean, which is 21. Mu, it's 21, right? Now, we said to the left and to the right of mu. So first we have, you see there's this mu minus sigma and mu plus sigma, right? So my sigma is, 0.5, right? So when you do, mu plus sigma, so mu plus sigma, that's like 21 plus 0.5, right? That will be 21.5, right? And if you do mu minus sigma, that's 21 minus 0.5. So that's 20.5, right? So here you have, there is 21.5, which is your mu plus sigma. And here you have your 20.5. So this 21, that's your 21. This is a mu, the mean. So on the left, so this 20.5, that's a mu minus 6. And you know, because this is a normal distribution, so here we have, this is a 34%, right? And here, this is 34%. Next, you have, mu plus 2 sigma and mu minus 2 sigma. So mu plus 2 times sigma. So that's like 21 plus 2 times 0.5. So that's like 21 plus 1. So that will be 22. And mu minus 2 times sigma. So 21 minus 2 times 0.5. So we have 21 minus 1. Right, that will be 20. So here we're gonna have like, this is gonna be like 20. That's mu minus 2 sigma. And here, right, you're gonna have mu plus 2 sigma, which is 22, right? This is 22 right here, and it's what, mu plus 2 sigma. Okay, and we know, because it's a normal distribution, because the age here follows a normal distribution. So here, so this area would be, as we said, right here, is the 13.5%. So here this is 13.5%. And here the same thing. This is 13.5%, right? Etc. So we can do, of course, the mu plus 3 sigma, mu minus the 3 sigma.
Is that standard, the divisions on the top, like 34%, 13.4?
Yeah, 30. Yeah, when I say 34%, that's a 0.34. So that's division. That's what, so when I say 34%, of course, I mean.
No. I know that's division. I'm talking about, would it always be divided that particular way?
Yes, that's what I'm saying. Yeah. So that's the thing about this normal distribution. So it's always divided like this way, like for normal distribution. So whenever you see, like in the problem, it's a normal distribution, then this would be a graph of normal. It's always divided like this. Yes. So we're gonna have always these numbers.
So it's always 34.
Yes.
Then,
Yeah.
13.5, 2.35.
Yes, always. Whenever you have a normal distribution, then that's the numbers you're gonna have. Yeah, all the time. The percentages you're gonna have all the time. Yeah. So yeah. All right. So anyway, so you can continue with the mu plus 3 sigma if you want. I mean, you know, for mu plus 3 sigma, you're gonna have 2.35. So let me just to have like a very numerical example here. So for 2 plus 3 sigma, sorry, mu plus 3 sigma. So mu again 21. That's the average, and the average age plus 3 times 0.5. So that's 21 plus 1.5. So that would be 22.5. And mu minus 3 sigma, etc. Minus, so that's 19.5. So here we're gonna have, this is 19.5. So that's my mu minus 3 sigma. And we're gonna have 2.35. So this is, oops. I'm supposed to use a different color here. So let's use yellow. So this is 2. Right here, 35. And the other side to the right of the mean, same thing, somewhere right here. And so this is supposed to be mu plus 3 sigma, and it's again 2.35. So this is like 2.35%. All right, guys. Now don't forget, the whole area under the graph is supposed to be 100, and so again, the graph is symmetric about the mean. So like to the left of the mean, you have 50%, right? And to the right of the mean, you have 50%, right? Anyway, so now let's come back to the question. So what does it say? The question, well, here we need to find the percentage of students with age less than 20.5, less than, right? So when you say less than, it means to the left, right? So when we say, so less than some number, so like in this example, less than 20.5, right? So that will be to the left of, this left of 20.5. Okay, so that will be the area to the left of 20.5. All right, now this is like kind of like, it's not like a geometry question, but so you need to think a little bit about it. So what will be the area to the left of 20.5? So where is 20.5? 20.5 is this. I'm gonna use the blue, I guess. So you see, this is 20.5, right? Remember, that's mu minus sigma. That's how I got the 20.5, right? This is my 20.5. Less than 20.5, we said that will be the area to the left of 20.5, right? Now, any guess what will be the area to the left of 20.5? What will be the percentage to the left of 20.5? So again, when I say to the left of 20.5, of course, I mean like this is where you have your 20.5, right? So what's the area to the left of 20.5?
Do you mean what follows?
Yeah.
Because it will be 20.
Nope.
The percentage 13.
Percentage. What will be the percentage to the left of 20? So if you say 13.5, well, but it's not exactly 13.5 because there's this area here, right? Here. So you're supposed to take the whole area to the left. So so it's supposed to be like this whole thing here, like right? Right. The whole thing to the left. So what will be the whole thing, the percentage or to the left of this 20.5? Just from this, like from this graph, like with these numbers. You're saying 60?
16.
Well, 16. Yes, very good. How did you get the 16?
It's hard to explain. It's divided into 2. So I picture it being okay. So 34% is already taken. So I would say 50 minus 34 equals 16.
That's very good. Exactly. That's 50% minus the 34. So just one thing here, guys. You see here it's supposed to be 13.5, right? And this is supposed to be here, supposed to be 2.35. But 13.5 plus 2.35, that's not the whole thing to the left of 20.5, right? There's this area.
There's the same number.
Right here. Yeah, there's this area missing, right?
Yeah.
So it's not exactly the area to the left of 20.5. So there is this area, you need to add this area. So, but what we can do is, because we know, so the area to the left of the mean, the whole area to the left of the mean, right? That's 50%. So to find our area, so what we can do is just to subtract, because this part here, that's 34, right? This part here, it's 34%, right? So then our area would be the difference between the 50 and the 34%. So that's the 16%. Exactly, yeah. So so then to answer the question here, so the percentage of students less than 20.5 is 50% minus the 34%. So that's 16%. Okay. Does this make sense to you guys? How I got this 16%? So the 16, it's not the 30. It's not the 30.5 plus the 2.35, right? That's not 16%. There is this area missing, right, to the left of 19.5. But what we can do again.
Question prior to
Yeah,
that.
please. Yeah, sure.
So before getting to that part, I was just noting what you was writing, but I know that we got the 0.5, the standard deviation from the problem. How do you jump from 0.5 on the second round when you're writing the problem? The number 2, like number 2, and then you wrote number 3. Does that mean like that section, like section 2 would be 13.5? So I'm gonna, okay, let me explain it better.
Say again. I'm sorry.
21 plus 2 times 0.5 equals 21 plus 1 equals 22. How do you get number 2?
The number 2, that's because,
yes.
Yeah, that's a good question. So you see here in the graph, so we said, because this is again, this is like sort of analog to this Chebyshev theorem, but for a normal distribution. So we have mu, but then the mean, but then we have like the mean plus 1 times the standard deviation, but then we have the mean plus 2 times the standard deviation, etc. So each time you multiply your standard deviation by yeah. So that's how I got that's why I have 2 here. So first I have, I have my mean mu, and then I have my mean plus 1 sigma, and then I have my mean plus 2 times my sigma, etc. So and then after that will be mean plus 3 times sigma, etc.
Okay.
Okay, that's why I have this 2.
Yeah,
It's just because of the mean plus 2 sigma.
Because I get what you're saying, but it's easy to forget.
Yeah, I know, but again, this is like, like in the Chubychev's theorem, for example. Remember we said like at least 75% of our data is between mu minus 2 sigma and mu plus 2 sigma. So this is an analog to the Chebyshev theorem, but this is for a normal distribution. But we use like multiples of the standard deviation.
It's more. That's what I meant. I just used the wrong words. It's like the other one. You have like 75%.
Yeah.
Whatever numbers I forgot. I don't have it on top of my head.
Yeah.
But this is the same thing. It's just you would do like 2, 3, 4 for.
So it's but it's.
So for the first one would be 34%. It will be 1.
Yes, that's like 1.
And then, and okay.
The thing is, the thing is about the normal distribution is we have like this is a better approximation than the Chebyshev theorem we had like in the section 3. This is a better approximation actually, because like between mu minus 2 sigma and mu plus 2 sigma, you have like 68 plus 27. So that's actually 95%. So between mu minus 2 sigma and mu plus 2 sigma, you have 95% of your data, not just the 75. Remember, Chebyshev theorem says like 75, your data is between mu minus 2 sigma and mu plus 2 sigma. So like here for the normal distribution, you have a much better approximation. You have like 95% of your data is between the mu minus 2 sigma and mu plus 2 sigma. Okay. All right. All right. So any other question, guys? Let me see the chat. I'm gonna just check the chat. Oh, okay. I see some things. Yeah. Okay. It's you, Yanni. All right. Oops. So this is you want to find percentage of students with age less than 20.5. All right, now let's do a different question. So instead of less, let's say we have more than. For example, so again, we have the same question. So now, so let's say you want to find the percentage of students with age more than let's say 21.5. 21.5 years. Okay, so when I say more than, so less than, of course, that will be to the left of, so less than, we said less than 20.5, that will be the left of 20.5, right? Now, more than, that will be, that's the area to the right of the 20.5, 21.5. So here, more than 21.5, that's the area to the right the area to the right of 21.5. Okay. Okay, let me just graph again my normal distribution. So we had, again, just to remind you what we have here. This is the mean mu, that's 21. And then we have here 21.5. So this is 34%. This is 20.5. That's 34%. And then we have, again, I'm gonna just use a different color here. So here it's 22, and this is 13.5%. Here it's 20, 35%, etc. And again, just to remind you, to the left here, to the left of the mean, it's 50%, and to the right of the mean, that's 50%. All right, so my question for you guys, what will be the area to the right of 21.5? The area to the right of 21.5. So the area to the right would be this, right? This is 21.5. So the area to the right would be this whole area here. Right, this is the area to the right of. This is area, right? This is the area to the right of 21.5, right? So any guess will be this area to the right of 21.5? Remember, the whole area under the graph is 100%. And again, the graph is symmetric about the mean, right? So we have like, there's 50% to the left of the mean, and there is like 50% to the right of the mean. So I guess it's not clear what will be the, I mean, just, just from the numbers here, it's not clear what will be the area to the right of this 21.5, right? So what we can do first to find this area to the right is probably you can try to find the area to the left of this 21.5. And if you find the area to the left of the 21.5, then the area to the right would be 100%, the whole area, minus the area to the left, right? So what I am saying here, guys, is that, so this area to the right, the area to the right of 21.5, that will be the whole area under the graph, which is 100%, right? It's 100%, minus the area to the left, area to the left of 21.5. Right, because the whole area is 100%, right? So if you subtract the area to the left, then you get the area to the right. Now, can you guess what will be the area to the left of 21.5? So the area to the left, of course, would be this, would be this area here. So let me see the chat if there is any guess. Okay. Well, so what we can do is, you see here, oops. Yeah, I think there is a problem with the Zoom. Okay, just wait a couple of seconds. All right, here's back. All right, well, as you can see, guys, so here to the left of the mean here, that's 50%, right? We said this is 50%, right? This is 50%, right? To the left of the mean. And then, so what's the difference with the left of 21.5 is this 34%. So the area to the left of 21.5 would be the 50% plus the 34% plus this 34%, right? So this is, so that will be this area, right? The 50% plus 34%. So the area to the left, okay, probably my graph now it's a kind of a mess. So let me just draw again here the picture. So so what I'm saying is, so here's your mean. This is your mean, 21, and we know this is 50%. Right, this is 50%. The whole area to the left of the mean is 50%. Now I have this 21.5, right? This is 21.5. And between 21.5 and 21, that's 34%, right? This is 34%. Right? So then the area to the left of 21.5, the area to the left of 21.5 would be the 50%. That's 50% plus the 34%. Okay. So the area to the left of 21.5 would be 84. That's equal to 84%. Okay. All right, so then we can answer the question. So that the area to the right, of 21.5. So that's 100% minus the area to the left of 21.5. And we just computed the area to the left of 21.5, and we said it's 84%, right? So that's 100 minus 84%, so that's equal to 16%. So that would be the percentage of students with age more than 21.5, right? So that's the age of the students. So that's the percentage of students with age more than 21.5. Percentage of students with age more than 21.5. So that's 60%. All right, guys. So we can, as you can see, so we can compute like a percentage of students to the left or less than some number, less than some age. Then we compute the percentage of students with age more than 21.5. Now, what about percentage of students with age between two numbers? So for example, what would be the age or the percentage? So find now, let's say you want to find the percentage of students with age between, let's say, 20 and 21.5. Okay, so just to remind you again that the graph we have. So again, it's a normal distribution. So something like this. So the highest point. So the graph is symmetric above the mean. That's 20. Our mean here is 21. The average age of the students is 21 years, and then we had this mean plus sigma. That's 21.5. So we said this is 34% right here. This is 21 minus sigma. So that's 20.5. And we have another 34 to the left of 21, between 20.5, 21. And then this is, oops. So this is plus 2 sigma. So that will be 22 here. So we have, again, here we have 13.5%. And right here we have 20, and this is 13.5%, etc. Right? We have, and then we have 22.5, and then we have 19.5, and this is, we said this is 2.35%, and this is another 2.35%. All right, guys. So, and yeah, and of course, to the left of the mean, we have 50. And to the right of the mean, we have another 50%. All right, so what's the percentage of students between 20? It's between 20 and 21.5. So here's my 20. Say it again.
No, you can go ahead.
Yeah, so between 20, this is my 20, right? Here's my 20. And 21.5, so that will be this. So here's 21.5. Right? So what's the area between these two numbers?
81.5%.
Yeah, absolutely. It's just yep. So that will be this area right here. So the area between so the area between 20 and 21.5 is, so we have, there is 13.5% plus 34, right? There's this 13.5, and then there's the 34, and then there is another 34. So plus another 34%, and as Yanin said, that will be 81.5%. So that's 81.5%. Okay. So that's the percentage of students with age between 20 and 21.5. So again, the idea, guys, is you need to find the area. And again, when I say area, it's just the percentage. Actually the percentage, when you say 34%, when I say 34%, that's divided by 100, that's 0.34. So the area of the region is actually equal to 0.34, right? And so the area under the graph, it's 1, which is actually 100%, right? But anyway, so yeah, so then so the area between the two numbers, these two numbers, 20 and 21.5, is exactly 81.55%. And so that'll be our percentage. All right, guys. Okay, so let's have another exercise. Exercise. This is just an example. Okay, so the first exercise 1. Exercise 1. All right. So just I'm gonna take an example or an exercise from the from the textbook. So we have the following. So the heights, so assuming, so this is exercise 7, page 302. Page 302. All right, so assuming that the heights of college women are normally distributed, so we assume, so assuming that the heights of college women are normally distributed. So here, guys, so in this sentence, so whenever you see normally distributed or normally, sorry, this is normally distributed. So when I say normally distributed, of course, I mean that the variable follows a normal distribution. So our distribution, our probability distribution, it's a normal distribution, okay? So then normally distributed with a mean, mu, right? Because again, here, this mu, it's a notation for the population mean, right? When you have like a sample mean, we use the X bar, but for population mean, we use mu. So this is mu, the mean, and so it says it's equal to 65 inches. And standard deviation, sigma, and standard deviation sigma equal to 2.5 inches. Yes, 2.5 inches. So the questions, what percentage of women, we have A, B, C, D. So A, so what percentage, I'm gonna just probably, so what percentage of women, so A, it says are taller than 65 inches. B, it says shorter than 65 inches. I don't think it's probably, that's probably easy. So let's say, yeah, let's do it anyway. So shorter, so they are shorter than, so instead of 65, it says 65 inches in the textbook. So let's say, for example, 60 inches, for example. Just take a different number. C, what percentage of women are between 62.5 and 67.5 inches. 67.5 inches. Okay. D. So D. So we have taller, shorter, are between. We can, yeah. Let's have another taller than. Let's say 67.5 inches. Okay. So of course, guys, when I say percentage of women taller than 65 inches taller mean more than, right? When I say shorter than means less, right? Just to clarify here. So when I say when we say taller than, of course we mean more than, right? More than. And when we say shorter than 60 inches or wherever, so that means it's less than. All right, guys. Oh wow. Okay, we have only like 4 minutes. Okay, well let's do at least the A. I think we have time to do the A. Well, you know what? I'm gonna explain how to get the answers because we have just like 4 minutes, so we won't have time like to. I don't think I have time to finish the whole exercise. But let me just say here. So first, this is a normal distribution. It says normally distributed. So whenever like in the exercise you see the word normal distribution, then of course we are talking about, so your variable is gonna follow a normal distribution, right? Then you have the mean. So here it says the mean is 65, right? The mean is 65, and your standard deviation sigma is 2.5 inches, right? So what we can do, of course, is because it's a normal distribution, we know we're going to have the following graph. So because it's a normal distribution, so as I said, this is always the case for any normal distribution. We're going to have like the percentages. So we have so again, the graph is going to be like, going to have like a graph like this here, right? And again, the highest point is going to be at the mean. Here, your mean, right? The mean mu. So what's the mean in this problem? It says mean is 65, right? 65 inches, right? The mean, it says 65 inches. So your mean is 65. So it's right here. That's your mean, right? That's, again, it's like the center of your graph. All right, now to the left of the mean, we're going to have like mu plus sigma. Here, we're going to have like mu plus sigma. So again, I'm going to have the same percentages. So that's like 34% again, right? And to the left, same thing here, mu minus sigma. And again, between mu minus sigma and mu, it's 34%. All right, now, so what's a mu plus sigma? What's mu minus sigma in our problem? Because sigma is 2.5, right? It says here, as you can see, sigma is 2.5. So mu plus sigma would be like, so mu plus sigma, mu is 65 and sigma is 2.5. So that's 67.5. So this is 67.5. Now mu minus sigma would be 65 minus 2.5, which is 62.5. So this is 62.5. All right. Then we have mu plus 2 sigma. So after mu plus sigma, we have mu plus 2 sigma. And between mu plus sigma and mu plus 2 sigma, again, it's 13.5%. Now, what's mu plus 2 sigma? Mu plus 2 sigma, that will be 65 plus 2 times, right? This is 2 times sigma. Sigma is 2.5. So that's like 65 plus 2 times 2.5, that's 5. So that's 70. So this is 70 here, right? And the other side, the same thing. So it's mu minus 2 sigma. And between mu minus 2 sigma and mu minus sigma, that's another 13.5%. And yeah, so mu minus 2 sigma, that's 65 minus 2 times 2.5. So the answer is 60. All right, so this is 60%. All right, so anyway, guys, well, you can think of this problem exercise. So next time I'm gonna probably go over this, and I'm gonna do more exercises and more details about the normal distribution. But let me just say, for example, here for A, it says taller than 65 inches. So as I said, when we say taller than, means more than, right? It's more than 65. So more than 65, where is your 65? Your 65 is right here. So more than 65 will be the area to the right of 65. Now the thing is, for example, here 65, that's the mean. So we know that the area to the right of the mean, that's always 50%, right? For example. So yeah, like, so for the answer for A, that will be 50%. Okay, because that's the area to the right of 65%. 65 inches, I mean, right? All right, guys, I'm gonna stop here. I'll continue with this next time, and thank you for listening, and hopefully I'm gonna see you next Monday. Take care, everyone.
Thank you, Professor. Bye-bye.
Thank
Bye,
you.
Professor.
Thank you, Anine.
Bye.
Bye. See you next week. Thanks.